While discussing the deposition of sediments in the sea, the concept of calcite compensation depth CCD, the carbonate saturation depth CSD, lysoclines are important. Let us try to understand. In the shallow sea up to around 3 kilometer depth, calcareous skeletons might be found within the sediment and can be called as calcareous ooze. Any calcareous sediment deposited below 3 kilometers, such as within this range, will be under partial dissolution. So, the thickness here will be less, and once one goes below 4 kilometer water depth in ocean, here we do not get carbonate deposits. The reason is this zone lies below the calcite compensation depth CCD, which is 4 kilometer. These numbers are average numbers given from the worldwide ocean, but from ocean to ocean these numbers can vary. What happens within this domain? Total dissolution of carbonates happen. Even if any carbonate is coming, let us say by some slide, will not stay for a long time. Whereas the shallow sea region is characterized by calcareous ooze, this portion is characterized by siliceous ooze and it can form chert. We do not get chert here, we get carbonates, and we get charts here and we do not get carbonates. Let us look at it once again. Carbonate saturation depth or calcite saturation horizon is the depth at which seawater transitions from being saturated to undersaturated with calcium carbonate. If the carbonate accumulation rate is shown by this blue color, then it shows that as one crosses the calcite saturation depth, which is at around 1.5 kilometer in some ocean, below calcite saturation horizon, the carbonate accumulation rate decreases, and lysocline is a zone and the depth range can be understood. This is 2.25 kilometer and this is almost 3 kilometer. That means within 2.25 kilometer to almost 3 kilometer depth lies lysocline. What is that? It is a horizon where dissolution becomes first noticeable. Dissolution was happening here, but then here within this zone the curve shows a fall and the dissolution has happened. As one crosses the lysocline, the dissolution becomes more rapid, and below lysocline can be called as the lysocline transition zone. And at about 4 kilometer depth over here, the carbonate dissolution increases extremely rapidly. And in this particular example, CCD is here at 4.5 kilometer depth shown by this place. Beyond that, the carbonate dissolution is extremely rapid and very little carbonate can be preserved. These are the meanings of the term lysocline, CSD and CCD. A carbonate platform is any shallow marine environment with carbonate sediments. Let us look at the carbonate platforms and the different kinds of succession. Let us define what is a carbonate ramp. It is a coastal slope with gentle less than 1 degree slope such as this, and over here carbonate has been deposited. The carbonate shelf, it is a platform attached to a landmass, and there are two types, rimmed shelf and non-rimmed shelf. In case of a non-rimmed shelf, carbonates are deposited here and it is not surrounding any region. This side is open, whereas in case of a rimmed shelf, here the carbonate mound is there, and in this way this portion of the sea is surrounded and it is called a rimmed shelf. There can be an isolated platform where the carbonate deposition has taken place in an isolated manner and we do not see any continuation. The facies distribution in the carbonate platforms, we can look the carbonate ramp. This is the one. We get inner ramp lagoon with wekestone and mudstone deposited here. Then comes the grainstone shoals, and then comes the packstone or the wakestones. Then comes the redeposited limestones, and then comes again mudstone or wakestone at the deeper water. So, these are the sequence of carbonates from shallower water to the deeper water. In case of a non-rimmed carbonate shelf, here is the example of the non-rimmed carbonate shelf. The different rock types of different varieties of limestones are presented and the deep water is mudstone. In case of a rimmed carbonate shelf, this one mudstone, wakestone, followed by grainstone, packstone, followed by reef bound stone, and then the rootstone, redeposited limestone, and finally the mudstone deposits are found as one goes from shallower water to the deeper water. How the successions will look like? In case of carbonate ramp, we get storm beds of redeposited sediments. Since it is in the shallow area, such coastal areas can be affected by storms. In the top there is grainstone, shoals of oolites and bioclastic materials. In case of a carbonate ramp succession, we get grainstones in the top portion of the succession, and in case of a rimmed carbonate succession, pelagic mudstones and carbonate turbidites at the bottom, and finally the reef bound stones at the top. Below reef bound stone lies the reef front rootstone brachia. Let us look at a carbonate depositional sequence or the attributes of a general carbonate depositional sequence. In this side is the textbook diagram, and in this side special situation with the carbonates. Here the three units have been identified: high stand systems tract, transgressive systems tract, and low stand systems tract, given by the different shades. This is the LST, low stand systems tract. This is the high stand systems tract, and then below that is the TST, transgressive systems tract. Going by the sea level variation curve, this is TST, which is here. This is the HST portion which lies over the TST, and the LST is shown in this place. These sharp lines indicate the facies variation. That means here can be a facies A, and here can be a facies B, here can be C, D, E. Across these zigzag lines are the facies variation. In between the TST and the HST lies the maximum flooding interval or the maximum flooding surface, shown by these dashed lines. In this diagram, between TST and HST lies the maximum flooding surface or the MFS. Different portions further can be presented. This is the place of lagoon, it is the place of platform margin, this is the peritidal region, this is the lower slope and basin, this portion is the upper slope. The sequence boundary is marked here at the bottom, and also here. That means TST and HST are bound by the sequence boundaries. In the context of sequence stratigraphy, three kinds of reefs can be described: the keep up reefs, the catch up reefs, and the give up reefs. It can keep up, it can catch up, or it can give up with respect to relative sea level rise. The keep up reefs keep track with the sea level rise and have uniform facies throughout. If a facies is identified at the bottom here, that is maintained throughout the succession. The catch up reefs have initial shallow water facies, then they lag behind sea level rise. That means the sea level rise is faster and the reef's rate of growth is slower. Therefore, the kind of facies we observe in the bottom portion of the catch up reef changes vertically up. However, when relative sea level, let us say, has been fixed, this facies again comes back over there. That means the relative sea level has gone static and the reef still keeps on growing, and then during this phase and this phase similar facies come back. Let us look at the give up reefs. They start to grow but are killed off by excessive nutrient poison, abundant fine sediment, suffocated or rapid subsidence below the photic zone. This means in case of the give up reefs, the sea level rise is much faster and the reef's growth is much slower. Therefore, too much height difference happens with the water column, and because of that unfavorable situation, the reefs can die and can get extinguished. They get suffocated. Suffocation happens because of abundance of fine sediments or because it goes below the photic zone. In the sea water, we can consider the depth up to which the sunlight can penetrate is called the photic zone, and below that the dark region is called the aphotic zone. In the photic zone, we get dissolved oxygen, but in the aphotic zone, we do not get oxygen. Let us also see some other terms of reefs in the context of sequence stratigraphy, aggrading reefs. What happens in case of aggradation in the classic diagram of sequence stratigraphy? Vertical or near vertical stacking or growth of sediment happens. If that happens on the reef, we call the reef as the aggrading reef. It constantly keeps up with sea level rise and remains submerged. This is the diagram. However, in the process of this journey, the aggrading reefs can be considered to be first the keep up reef, then the catch up reef, and then finally the prograde situation. In the keep up reef portion, in the adjacent sedimentary unit, one can find the transgressive systems tract. In the catch up reef portion, if one goes to the adjacent sedimentary rock, it is the early high stand systems tract, and in the prograding part, in the adjacent sedimentary rock is the late high stand systems tract, and finally the top layer, the top boundary is marked by LST, which is the low stand systems tract. This TST, EHST and LHST and LST can be pointed out within the sea level curve. TST, transgressive systems tract, can be identified within this portion of the curve. EHST, early high stand systems tract, can be identified within this portion of the curve. LHST, the late high stand systems tract, can be identified within this portion of the curve, and LST, low stand systems tract, can be identified within this portion of the curve, which means this portion to this portion has been considered as high stand systems tract, and this portion has been broken into two parts, as this part as the early high stand systems tract and this portion as the late high stand systems tract. This early and late division I am showing first time in the context of reefs. So, vertically upward in case of an aggrading reef, the sequence is KU, CU and then PR, and corresponding sequence stratigraphic aspects are TST, EHST, LHST, and then over the top of PR is the LST. Let us look at the compound reefs. Here the stacking pattern is not vertical. In the previous case, aggradation, mostly the stacking pattern was vertical, whereas in this case we can see the stacking pattern is non-vertical. Stacking pattern of different parts of the reef is not vertical, also is shown here. In this diagram, this is the land side and this is the basin or seaside. So, the stacking gets tilted and it goes towards the basinward direction. As in this case, KU followed by CU followed by PR, same thing happens here, KU followed by CU followed by PR. As in this case, KU and TST, CU and EHST, PR and LHST, same thing happens here, KU and TST, CU and EHST, PR and LHST. These reefs are produced due to aggradation followed by progradation, and this situation can develop when the amplitude and period of sea level fluctuation was moderate or when the reef growth could easily match the fastest rates of the sea level rise. As you see, the stacking is non-vertical, they are prone to slumping or prone to failure. Depending on the ocean waves, Depending on the coastal wave energy, the compound reef may break and slump. We can say that the TST reefs are mostly keep up. EHST reefs are catch up, as we have seen in the previous case also, and LHST reefs are prograding. Now, we are going to see the prograding reefs, and we are going to consider a rise and fall in sea level. From here to here we will consider sea level rise and then the sea level fall. Here we get Cu, PR, again PR and PR, Cu, PR, and which goes on. We do not get Ku, which was earlier found for a compound reef, and Ku, which was found for the aggrading reef. So, in this case, no Ku, no keep up reefs was found. It is catch up since beginning. Here also the stacking pattern is non-vertical, as also shown in this simple diagram 1, 2 and 3. In this case, the sea level change is minimal. Since the sea level change is minimal, the reef can get good amount of time to adjust its height. I mean, it can increase its height, and this sea level change can be of long duration. Since we mean that the sea level change was minimal, note the sinuous curve, it is not that strongly sinuous as in this case or as in this case. So, deliberately the sinuous curve is drawn more open and less curved. Where the LST has developed, a slight downshift in faces can be noted. This is the downshift. The reef builders could easily exceed the rate of sea level change. Let us look at the retrogradational reefs. Here we are going to see 4 instances, 1, 2, 3 and 4, and these are those spots within the relative sea level change curve. Here we get only the give up reefs at the bottom. What happens in this case? Relative sea level rise outpaces the reef growth. The relative sea level rise is very fast and the reef cannot grow so fast. So, there is a huge difference, and a long water column lies over the reefs which are present here. There can be suffocation and other issues when the reef actually dies, and in this the reef's growth is severely affected. In this case, the reef moves towards the landward direction and the stacking is non-vertical. But once the system catches up, once the reef catches up during a high stand phase, progradation dominates. Beyond the maximum flooding surface, beyond this point and in the younging direction, the reef stacks up in opposite direction, and this is the time when progradation PR is happening, and that is what is stated here. During high stand, the reef can catch up. 1, 2, 3 is a time when the sea level rise was happening. At 4 is a high stand and the maximum flooding surface, beyond which the sea level keeps falling. Then this column of water keeps reducing its height. I have already discussed in this kind of diagrams about the progradation, retrogradation and aggradation. Now, these terms we are going to see in the context of a carbonate factory where a carbonate mound is considered. Consider T1 is the level of sea surface, and at that time this was the carbonate level. Now, when the sea level rose to T2, this became the elevated mound, and when it became T3, this became the elevated mound. This kind of geometry can be clearly be understood as an aggradational type comparable with this scenario, where we see if I move vertically from any point from the bottom, we get similar kind of lithological variations. Let us take the retrogradational case applied on carbonate mound. From T1 sea level, it has gone to T2 and then to T3 shown by arrows. In this case, the kind of mound growth is different. At T1 time, this was the geometry. At T2, it has gone like this, and in T3, it has gone like that. So, not only the mound is growing vertically, growth of the mound is different from that of the aggradation case. So, this is a case of retrogradation. Now, let us take the case of progradation in case of a carbonate mound. Again from T1 sea level it has gone up to T2 and T3. This time the growth of the mound is not much upward. Yes, it has gone up no doubt from T1 to T2, but clearly there is more of spread. This is the case of progradational situation. So, in this side was the carbonate mound. These are the classic sequence stratigraphy case.